My name is Amy Perfors, and today I'll be telling you about some work I've been doing studying decision making in Black Swan type events, which many health situations are. So, as a motivation, consider this situation faced by a lot of parents nowadays, which is whether they should send their kids to school given the coronavirus. Now, this is in many ways what we might call a black swan problem. That is a problem where there are reasonable odds of having a moderate gain of something, but extremely low odds of having a major loss. You can replace losses with gains and the same kind of thing. And many health decisions have this form. So both decisions about sort of behaviors that have health implications, like riding a motorcycle, deciding whether to vaccinate or not, deciding whether to have certain surgeries, for instance, and of course many of the decisions we're faced with in the coronavirus are black swan type things. Now you might ask at this point, aren't black swans well studied? And indeed, if you Google it, it sure looks like it. Much of that work, though, is in economics and in psychology. If you look at actually experimental studies, there's actually very little where they look at things that have extremely low odds and the loss is catastrophic. So the odds rarely go below 1%, and the losses are generally not that bad. And so what I'm interested in is basically situations like that. Now you might ask, what about having very, very low odds or really bad things makes them qualitatively interesting or distinct from other types of decision problems? And I think there's two things. One is the fact of having very small probabilities has interesting cognitive implications, one of which is the problem of representational resolution. How do we represent these really, really small probabilities? And there's evidence that people appear to represent them in a fuzzy way and much more qualitatively, and so they're not exact. And one implication of this is that people might reason very differently about a situation like this, where they're choosing between two options, one with a risk of 0 and one with, say, 1 in 1,000 risk. They don't differ by much, but if they qualitatively, if they're encoded in a qualitatively different way, they might really try to avoid that 1 in 1,000, even though it's tiny, and even if it has greater benefit attached. Conversely, if you have two options where both of them have a tiny risk and the magnitude of the difference between them is large, but they're both very tiny, if people are representing that, they might actually treat them very similarly. So that's one implication. The other thing, though, is about the utilities. When the utilities get very bad, it's hard to know how to quantify them or estimate them. How do you quantify how bad is death or severe illness or disability? That makes it really hard to model, but also we don't really know how people think about that. So what I'm going to be talking about today is two sets of studies that address these. The first is about small probabilities, rather wanting to see whether people are sensitive to these tiny changes in magnitude, what that means about their risk preferences. And secondly, about sort of how they quantify and estimate utilities, particularly in the realm of vaccination. All right, so for the first problem, I'm going to be reporting on a series of experiments that all have very similar method. We take people on mechanical Turk, give them a random set of starting points. Each person gets only one. And they're told they get paid a bonus depending on how many points they have at the end to incentivize making a good decision. Make sure they really understood all of that. And then ask them each one question and one question only. So this is all between subjects. We say, okay, you have this many points. Please choose between the following two options. And we don't tell them it's more risky or less risky. That's just for you guys. And then we just see what they choose. So what are the two options? Well, in one condition, which I call the one risk condition, the more risky option, basically, there's a gain of 15 points, so it's a reasonable gain, but a tiny, tiny risk of losing all the points. And in the less risky option, the gain is smaller, but there's no risk of losing anything. And the difference between them is about 10 and 10,000. Now, in the two-risk condition, it's very similar, except that this time, and in fact, the more risky condition is qualitatively identical. But in the less risky condition, this time, there's a tiny, tiny, tiny chance of losing everything. So 1 in 10,000, right? The difference between them is, again, is very similar in magnitude, if anything, slightly larger in the two-risk condition. Now, if you put these into expected utility theory, you can see that they're qualitatively identical between both conditions. And the prediction is that if you have more than 5,000 points, you should choose the less risky option, and in the otherwise you should choose the risky option. The point is, though, that both conditions are the same expected utility-wise. So if people aren't encoding small probabilities, we would expect them to sort of treat the one risk and the two risk conditions as a qualitatively distinct way, because one risk has none and the two risk doesn't, and that they shouldn't represent the difference between the more risky and less risky option very precisely, which predicts that in the not one risk condition, people should be more risk averse because that's a zero risk, even though the risk of the other thing is very small and the gain is more. And it predicts that in the two risk condition, they should shift to being more risk seeking, especially relative to the one risk condition, even though it's actually much riskier. And it also predicts if people aren't encoding these things, they should make the same decisions regardless of how many points they have to lose. Whereas if they are encoding things, you should find no difference between risk conditions, and also they should change their behavior as the number of points they have to lose changes. All right, so what happens? First, let's look at the choices people make in the one risk or two risk condition. As you can see, they do shift to being more risky in the two risk condition, and you can quantify the magnitude of this shift. That's basically the size of that arrow there. And also, if you look at how they change their behaviors as a function of the starting points, there's really no difference in either the one risk or the two risk condition. They're indifferent to the magnitude. So basically, all of the predictions of the theory that they're not encoding small probabilities are upheld. Now, you might ask how robust this is. So I showed you one experiment where the magnitude of the risk was basically 1 in 1,000. So I did 4 more experiments verifying this. So there's one where it's 1 in 100, one where it's 1 in 10. In both of those, that shifts the expected values, so you should choose less risky in both conditions. But again, both conditions are the same in terms of the pattern. And in experiment 4, I made it very, very small, 1 in 10,000. So this is tiny, tiny, tiny. And this says in this condition, you should actually choose the more risky option all the time. The real question is whether you see that risk shift in all of the conditions, where people are more likely to choose the risky option in the two risk condition. So as a reminder, that is what we saw in experiment 1. You saw that risky shift. See the same thing in experiment 2, qualitatively very similar. In experiment 4, people are indeed choosing the less risky option more, but you still have that risk shift. And in experiment 3, they're choosing the riskier option more, but still also having the risky shift. So basically, we're seeing the risky shift in all of the conditions. And also in all of the conditions, we see an indifference in magnitude. None of these things are significant. So basically, the predictions of what we'd expect if people aren't encoding small probabilities are upheld throughout. And this does suggest that we would expect people to be more risk-seeking when both options have non-zero risk. The interesting thing is, even if that risk is minuscule, even if it's 1 in 10,000, or indeed 1 in 100,000 in the two risk case in one of the experiments. And so one implication here is that perhaps risky health behavior comes from this perception. If the idea is you can't actually get it to 0, then why bother? And that's why people act very risky sometimes. So that's the first part of today's talk, talking about the implications of small probabilities. Now I want to move on to this question about quantifying the utilities, and I want to do it in a situation that comes up all the time and understanding how people reason about vaccination. So let's try to apply expected utility theory to vaccinations. You have choices, 2 choices, don't vaccinate or vaccinate. If you don't vaccinate, you pretty much have to figure out what's the chance of getting a disease like whooping cough that you could have vaccinated against. How bad is that? And if you do vaccinate, then the question is, well, what's the chance of some negative outcome, say autism? How bad is that? There's maybe some milder outcomes like high fever, which is slightly higher chance, but not that bad. And then, of course, a certain chance of no change. So this is the decision you're faced with. And what we wanted to do is basically just estimate all of these things. What do people think about these probabilities and the utilities? Not what are they actually in the world, but what do people think they are? Because that's what they're probably using to make their decisions. So we asked a bunch of people again on Mechanical Turk to estimate these probabilities. So first we asked, what's the probability of a child developing whooping cough if they don't get a vaccination? You can see this distribution of responses. You can see it's all over the map. The modal one was about 5%. We also asked them what's the probability of developing autism because of a vaccination. Somewhat nicely, the mode is 0, but there's a fairly substantial second mode, which is fairly of 0.01. And this actually creates a situation that's pretty analogous to the 1 risk versus 2 risk conditions in the first half of the talk, where the 1 risk is if they believe the probability of getting autism is actually 0, then we can drop that out, and the vaccinate decision looks like something with at least no real catastrophic risk. However, if they do think the probability of getting autism is non-zero, then it ends up looking a lot like the 2 risk condition. The don't vaccinate option is very similar, but the vaccinate now has this other tiny chance of this autism outcome. So now the question is, well, what are the utilities? How catastrophic are these things? And we asked people to estimate these by having them answer relative questions. People are really hard at putting a single objective number, but it's a lot easier to say how much worse something is than something else. So if you ask people for whooping cough or high fever, which is worse, you can say most people thought whooping cough was worse. And if you ask those people how many times worse it is, you can see that the modal response is about 10. So that suggests that, for our numbers, we'll put in that the utility of whooping cough is basically 10 times the utility of fever. These are all negatives, so it's 10 times worse. So putting those numbers in, all that matters is the relative thing. So I said, say fever has a utility of negative 100, then that means whooping cough is going to have a utility of negative 1,000. All right, how about autism? Now, most people said autism was worse than whooping cough. And if you actually ask them how much worse is it, most of them, the modal response was that it was 10,000 times worse. Again, if you put those numbers in, then what that means is basically that this sort of utility of autism down here in the lower right corner is negative 10 million. All right, now let's just calculate those numbers. If you calculate these expected values, it suggests that if you see the probability of autism as 0, then you should probably vaccinate. If you see it as not, and you think autism is that bad, then you definitely shouldn't vaccinate. Now, we asked whether people actually, if given these numbers, they reason in accordance with expected utility theory. So if you ask them just without the vaccination framing, with just the numbers, indeed they do. They choose to vaccinate if given the numbers in the 1 risk condition, and in the 2 risk condition, if you give them those numbers, they choose not to vaccinate. Again, it was without the vaccination framing. This is just the numbers. So as long as people think in these ways, the implication is, even by expected utility theory, they shouldn't be vaccinating. And this is very robust. If they think autism is that bad, even with a tiny PA, a tiny probability of it, then the reasoning is the same. And so what this all suggests is that if we want to change people's minds about vaccination, instead of trying to change their estimates of the probability of autism, maybe the thing to do is change their utilities. Do education about how whooping cough, measles, and stuff are much more terrible than they think they are, and possibly that autism isn't quite so bad. So to sum up today's findings, we basically did 2 different types of studies. One, looking at the implications of small probabilities, suggested that people really reason qualitatively differently about something that has any risk, even if it's tiny, 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 and then ask implications for their risk aversion. And secondly, that if you're looking at sort of people's reasoning in a vaccination context, it suggests that that some of their behavior may be driven by their sense of how bad autism is relative to whooping cough, and that might be a target of intervention. All right, thank you very much.